two very special speakers for me. I'm now going to introduce another person who, in fact, is a friend for quite some time now, and he's one of the most frequent speakers at LACNIC. For me, he's doing an amazing job. I don't know whether you have been looking at the IPv6 reports that we have seen, among many more things that he's doing for the community and the studies of very high quality. So this time he's going to be speaking about the reflection of MOAS BGP in the LACNIC region. I think this is a very interesting topic. This is the very first time we touch upon this topic in the forum. So let's welcome Alejandro Acosta. Hi, good afternoon. Thank you very much for your introduction, Jorge, and Carlos, for the previous presentation, because this sort of paved the way for me with my presentation. One of my slides includes something regarding route views. I'm going to speak about MOAS, the first time that we discuss this topic in this event. So when we start with a topic like this, we say, what is a MOAS? And very briefly, this is multiple origin autonomous system. And I'll explain what this is about. This doesn't seem to convey very much, but specifically when speaking about MOAS, I first want to speak about two BGP concepts that I'm almost sure that most of you know what it is. But this is so to provide a setting so we're all on the same page. The first concept is that this is an AS path. So this is an attribute. I like to compare this with a label. Imagine I'm going to say something to Carlos, to Jorge, to Jordi, to Andres, and I put a label onto it. It's like when you send something by courier and say, well, this side up, this is fragile, and I place a label on it. In the BGP world, there are some mandatory attributes. AS path is a mandatory attribute. Each update packet has to have this attribute. And what is this? This is an organized list of all the ASs through which a route goes from origin to destination. And this is very interesting and will depend on where we are. This was something that Carlos mentioned too. So there are different collectors in different parts of the world, because not every router will be seeing the same picture of the internet. In Chile, you might see it in a way, from El Salvador in a different way, and the same for Uruguay, and so on. This is a small example. For example, here we have an AS path. You might say, well, all those numbers. So each of these numbers represents an autonomous system. And I'm interested in highlighting that the one further to the right is the origin autonomous system. The other autonomous systems are the ones that it goes through in order to reach a destination. This explains some more details, but let me very briefly mention that the one on the right, as I said, is the origin autonomous system. And what is the origin AS? The autonomous system number of origin in BGP refers to this autonomous that originated the route, the path. So if the gentleman works at a university and has a prefix, has an autonomous system, you announce this. And this will be learned by the upstream provider and so on until it reaches the destination where you receive the full path. This is another prefix. It was taken from a routing table, a BGP table, rather. It's 2001 DD8 colon 8 colon colon 1. So what is the origin autonomous system? The one on the right, 11164. The upstream provider at BGP level is 46437, then 1221, and then 4608. But let us focus on this little number over here, the origin AS. So far, so good. Okay, Alejandro, you're tiring me. I knew all about that. So let us take a step further. So what is MOAS? And this is what the topic of the presentation. MOAS is the announcement of that same prefix from different autonomous systems. In fact, here people have been speaking about the opposite. In fact, You have autonomous systems in different sites and announce different prefixes. Now, in this case here, this is the same prefix from different autonomous systems, 2, 3, 4, as many as you wish. Some might say, well, this breaks my prefix, it breaks the internet. So let us explain this briefly. This slide, and at LACNIC, is one that we use all the time. We use this very, very much. And I like this slide because it explains how the internet works. I will go through it in a decently rapid way, but let me explain how the internet works. Here we have all the different routers. For the purpose of this router, each of the example of each is an autonomous system. We have the AS300, which is the one on the right, and it will go decently rapidly. Autonomous System 300 announced a prefix and added a label, the mandatory attribute, which is the AS path, AS300. This was learned by AS200. AS200 announces this to AS100. AS100 announces this to 2 autonomous systems, AS500 and AS400. And look at how this is growing, how the AS path is growing. The one further to the right is the origin AS path, the one that originated all the rest over here. And all of them learned this. Now, the beauty of this, of MOAS, is that this is happening from various internet sites, like with the AS origin. It sort of surprises us, but exists a lot in the region. And this is like an exam question. Who originates the announcement? AS300. Who are the neighbors or pairs of AS100? Let us recap so we're all on the same page. AS100 is this one over here, and the neighbors are AS200, AS500, and AS400. 200, 400, 500. Who propagated the route? It's those who learned the route and who have pairs to announce these. They don't have pairs to announce it, so it is AS500 and 600 don't appear, so this is meaningful. And who learned the route? All of them did. The one that originated and those who learned the route through BGP. Regarding the study data, for the purpose of this BGP study, we used, unfortunately, we didn't use route view, but we used Potaroo. This is quite a famous one, and I like to use this because we have an image of the BGP table viewed from Asia. So I think this is one that I have been using a lot in the LACNIC GitHub. We even have scripts in Python that can use these BGP tables. They raise this to Python sites, and these can be processed quite well. So that you know, this study was done with IPv4 and IPv6 tables on December the 12th, 2025, not so long ago. And how many prefixes were processed? 235,000 in IPv6 and more than 1 million prefixes in the IPv4 world. So let us have a look at real MOAS. What is really happening in the internet?
Here we have a prefix, 2001 468 1F0C semicolon slash 48. Many of you may have done this. This is in BGP showed in the world of Cisco, Quagga. The output is quite similar. Of course, the different vendors may put it a little bit different. And here they're telling me that this prefix has 4 different ways, but I'd like to highlight the A's of origin. So this is being announced by this number 396955, and in another path we have the areas of origin 116164 from 2 autonomous systems. And here I have 2 perspectives. Here I have another type of outputs. So here route view, well, here you have IPv6, the prefix of origin, and here you have the other one. So I think that we all understood this. And the other example is this is a prefix of LACNIC that is being announced from different autonomous systems. So, why do we have MOAS? In a nutshell, I would say that it's because of traffic engineering. That is the short way of describing it. If I were to explain the entire thing, we would have to I'll leave it here. Well, my data migration, Anycast, whatever we want to put it. But let's say that it's traffic engineering, and some of you must maybe using it at present. Now, if you say, well, I have to indicate the prefix, what is the autonomous system that needs to announce it. And fortunately, the people that did RPKI thought, well, I don't want to use four-letter words here, but well, they thought of almost everything, and they said, well, I hate to read very long thing, but it says, in the context of RPKI, Resource Public Key Infrastructure, it's possible to create multiple ROAs, route origin authorizations for the same IP prefix. Let me translate. All of you have created ROAs, I'm sure of that. And what can you do if you have a prefix? You create a ROA, and I say the autonomous system that can announce it. Are there other autonomous systems that can announce it? I create another ROA indicating another prefix. That works perfectly well. The RPKI validators, and they do the router validation, and they're going to accept it with no problems whatsoever. So fortunately here we are well covered. The MOAs, are they good? Are they bad? So let's talk of the advantages and the disadvantages of the MOAs. What are the advantages? I mentioned some. Redundance, resilience, there's no doubt about this. If I have a prefix in the autonomous system and all of a sudden one fails and the autonomous system falls, crashes, it's going to be announced by another one. And we're speaking of the IP service traffic. Services are another thing. Authorization of traffic and anycasting. This is a perfectly valid concept. I can announce it. I can announce the same prefix and it would work. And the behavior of BGP as such will make the traffic be taken, directed to the closest one. That is the Anycast. If you want to migrate and a soft landing, you can use this mechanism. That can be an interesting solution. What are the disadvantages? Complexity of troubleshooting. When I wrote this, you say, well, but troubleshooting an autonomous system with traffic, imagine if I have 2 or 3, things can get very tangled. It's not so easy. Coordination between ASNs. If you have 2 or 3 ASNs with the traffic, that's okay. But if I have more, I have to tell Santiago, please announce the prefix, but this evening, but with Le Prepend, with this community, it's more difficult to do. I'm not saying it's impossible, but you're adding complexity to it. And finally, again, the word complexity, it's complex to monitor. In the website, you announced an autonomous system. So am I announcing this ASN or this other one? So the issue of complexity of monitorization. Well, I'm not saying you can't do it, but you have to try harder when you want to monitor the objects that I want to monitor. So those are some of the pros and cons, and then you may think of others. So let's go through the statistics. And when we conducted this study, this is a study that we decided to carry out in LACNIC in 2024. We decided to do it this year. When we started it, well, you said, well, from the perspective of LACNIC, the statistics that we're going to show are based on LACNIC. What does it mean? The prefix is LACNIC and I don't care about the SPAF, or do I care about the ASN of origin and just that? Well, so it wasn't easy to decide what to consider. So at the end we said, well, any aspect of the prefix or the SPAF that touches LACNIC, we should care about it. So this is a part of the complexity. Later on, I'm going to announce another one that was also hard. So statistics, traditional MOAS, and I'll explain later why I use that word. It's the MOAS that we've seen so far, the same prefix of several autonomous systems. In IPv6, in the global BGP table, we got 909. In IPv6, and for IPv4, 1958. That's what we got. And the number of ASNs used in MOAS for the same prefix, the same value for IPv4, IPv6, that's easy. 3. We got the same prefix and it was announced in 3 different ASNs. What else do we have? ASNs that participate with more MOAS. There we see, I won't describe the details. There's here in IPv4, well, the people that works with MOAS, they like to do MOAS because there's a lot with SPAFs that are participating with those autonomous systems. And if you look at it with the magnifying glass, I entered in the table hundreds of thousands of times, and we're going to see that many of them, in many situations, they say, no, in our country, sometimes they are providers, others are in transit, but sometimes it's themselves. They have the infrastructure put together so that it will run well. In the case of LACNIC, how many LACNIC ASNs participate in MOAS? 158 in IPv4 and 61 in IPv6. Notice how it's drafted. How many ASNs of LACNIC participate in MOAS? Another perspective. ASNs of LACNIC. This is how many prefixes of LACNIC are in MOAS. In IPv6 we get 85 and in IPv4 22. Remember that those 85 would be of the almost 150,000 IPv6 prefixes that we analyzed that correspond to LACNIC doing MOAS. And IPv4 22, and of the about 1 million we had. So what are the prefixes of LACNIC, where at least one AS belongs to LACNIC? The prefix of LACNIC, we went through all the autonomous systems and we went to see which was of LACNIC. In IPv6, 15, in IPv4, 8. Something that we can conclude here, and I'll mention it later, is that we see that MOAS is much more used in the IPv6 world, and I checked this hundreds of times. Another one, MOAS presentations in prefixes in LACNIC, and all the autonomous systems belong to LACNIC. In IPv6 we got 4, in IPv4 7. Okay, ASNs of LACNIC, we got this autonomous system. Here it appears 6 times, and the ASN of LACNIC most repeated in MOAS IPv4 is 61945. It appears 14 times. I don't know whether the administrator is here. Okay, and here we have a very interesting issue. Traditional MOAS. If you look at the MOAS studies in the internet, this is a very novel concept, but there's very little material in the internet, very few studies. What happened a month ago? So this work is quite advanced. I said, well, what happens if I have a prefix, for instance, in IPv4/20 announced from my autonomous system, and all of a sudden, Sylvia announces a /22 of my same /20. It's a MOA. What would happen? I didn't see it in any of the studies that I read. And I called it MOAS CIDR. Here you have an example. Here there's a prefix /32 with this path, and we see there's a /40 that belongs to this /32 with another path, again with a different alias of origin. If you remember that the BGP table has 235,000 prefixes, more than 20% of the table is CIDR MOAS. It seems crazy. I got hundreds of prefixes. I checked it, and this is the figure I got. It was exactly 535 out of the 235,748 in the IPv6 BGP table. What else do we have? Another thing that I thought that are there any MOAS of MOAS? Let me summarize it in closing. Yes, there are. What is a MOAS of MOAS? I have a big prefix, a /26, that is announced by 6461. There's a /32 that belongs to the /26 that is announced by 6509. And there's also a /40 that is announced by 8111 that would be inside the previous /32. And I got an example of 18 levels of announcements like this. How many cases of MOAS did we get in the IPv6 table? Specifically, 180 cases. What else do we have? Summarizing, the use of MOAS is not a technique that is either recommended or rejected. Please, so don't all go to ask your good friend that administers routers not to use prefixes. I'm not saying it's good or bad. I'm just saying it exists. And if you use MOAS, you're recommended to have a high expertise in BGPs. You have to know how it works well. The MOAS practice in the region of LACNIC is a reality, and not everybody needs MOAS. And as a matter of fact, I'd say here, as a matter of fact, it's for a minority of people. And when I saw these statistics, I was wondering whether we are seeing a boom of MOAS in the IPv6 world. So, that's all I have for today. Any questions or doubts? Questions for Alejandro? Hello, I'm Ivan Morales from Guatemala. Alejandro, is it possible for part of those MOAS, could they be configuration errors? Yes, I think so. But I don't know how many. It's absolutely a possibility. But I think that minority of the MOAS, but some of them may be. I wouldn't speculate how many. So could we say that these are route links that look like MOAS? Well, you have to sit down, and I don't know whether you know anybody who has this practice. I would like to even call them and see why they do it. What are the pros? What are the advantages? Having done this, you need to speak to somebody who has done this in real life with real services. Congratulations. That was a very interesting presentation, and hopefully this may open people's minds. People may realize that this is not meant to everyone, and if you find anything that affects you, because it could be an error or somebody that's doing something with their IPs, please report it or do something about it. Thank you.
Thank you, Ivan. We have Jose Gregorio over here, and then Julio. This is not a question, this is a comment. Great question, Ivan, and my comment goes along the same line. Sometimes I think you have MOAS, and I think there should be an amount, a higher, big or small amount of MOAS that we don't know are happening. Let me give you an example of something that happened to me with a provider with an ISP in Argentina. We have major provider. The traffic went with a quote-unquote normal publication with the origin ASN. The upstream was propagated without any issues, and then we included a secondary provider. Now this secondary provider did BGP with a private ASN. They didn't want to do the BGP with a normal ISP ASN, and evidently that second provider did prepend and eliminated the private ASN, and in that case the same prefix went out through the two providers with a different ASN, one with a natural ASN and the other with the ASN of the other provider that did BGP with a private ASN. So I'm sure that there will be MOAS where the manager for some reason either doesn't know that that's it happening or it is inevitable to occur. It's need to be intentional. Just that comment. Thank you, Jose, for your comment. Hello, great presentation, and in line with what I was listening to when you explained the different cases. I wonder whether you could this study you're carrying out can be complemented and crossing the information of the MOAS that we have and the prefixes that have RPKI configured to validate the origin. And so that in that way you could have an idea or a precedent as to which are those announcements that are validated, they're announced and are not errors regarding how they originated. Thank you, Julio, and that is a very good comment. Very often MOAS can also be a network hijack. There can be other things behind it. So it's interesting to explicitly cross this information with the validity status of a prefix with RPKI. Yes, I like the idea. So we have no more questions. Oh, Celsa, yes, one more question. Hello, Ali, great presentation. I wanted to ask you if you have a theory as to why in IPv6 there are so many MOAs, and also a comment. I have come across cases with internet providers who have different autonomous systems, or very often these are acquired by other organizations with their own autonomous systems. So this could be a scenario where this type of situation might occur.
Elsa,
Thank you, Celsa. Part of the question was why there are so many MOAs in IPv6. Well, I tried to look this up, and I would dare to say that traffic engineering that allows the addressing space in the IPv6 world is enormous. So any operator that receives a /32 can, without any issues, subnet a /36 or 40 or 44, 48. And of course the intermediate bits, and technically that is also possible. But basically, traffic engineering with IPv6 is excessively much higher than in the IPv4 world. And the second part of your question, I got lost. Can you repeat this, please? No, this was that there are cases in which one single ISP or internet provider has different autonomous systems, or sometimes a major ISP wants to have another ISP, so they inherit autonomous systems, and maybe this could be one of the causes that explains so many. Yes, that is a very valid option. It results from a merger or acquisition. They have two autonomous systems, and they figure out how to solve this. So as you see, Alejandro has a lot of work to do ahead. So thank you very much for your presentation. And let's give Alejandro an applause.